Hi, my name is Alex Gervich, one of the co-developers of Firefly. In this video, I'll be showing you how to create your own Firefly data files so that you can visualize your data in Firefly. The Jupyter notebook that I'll be going through is available online in our documentation and ships with the Firefly code in the Firefly notebooks directory, and is called Reader Tutorial. So let's get started. The first thing that we're going to do after importing is create a reader instance. The reader class is intended to collect all of the different Firefly classes that create data files and link them together in a filenames.json file. All of those files that it creates will be output to the JSON dir. Your browser has a security protocol that restricts its ability to read files that are not a subdirectory of the web page that it's currently visiting. This is to protect you from going to a random web page and having it search your entire file server, which would obviously be bad. As a result, all of your data has to be readable from the Firefly static data directory. If your JSON dir is not a subdirectory of the static data directory, then we'll create a symlink for you automatically. But note that this won't work if you're trying to run it live on the internet. This will work if you're running it locally on your own computer, but you'll need a hard copy of your data saved in the static data directory if you want to run it on the internet. I'll go over this in more detail in another video when I talk about managing multiple datasets. For our purposes, however, we'll just go ahead and save our tutorial data in the static data directory. So now that we've created our reader instance, we're going to create some example data. Here I'm just using a grid, a 3D grid of coordinates with some random field values. Now that we have our data, we're going to store it in a particle group. Particle group takes as its first argument the name of the particle group that will be shown in the user interface, and its second argument, the coordinate data. Everything else is optional. Here, I'm setting some settings, like the initial size and the initial color of the particles. Go over how and what settings you can set in another video dedicated to settings. But for our purposes, what's more important are these tracked arrays and track names. Here, we're passing in field data and naming it. Down here, we've made a copy of the data in a second particle group, but I've also provided the decimation factor equals 10 keyword argument, which will allow us to store all of the data in the particle group, but only output to JSON files 1/10 of it. So we'll see that in just a second. Note that there are some warnings being printed here because I've taken advantage of the default behavior that when you pass in fields without specifying filter and color map flags, that it assumes that you would like those fields to be filterable and color mappable. If you would not like those fields to be color mappable and filterable, then you should use the tracked filter flags and tracked color map flags keyword arguments. Moving on, now that we have created our particle groups, we have to link them to the reader using the add particle group method. Once we've done that, you can print out the reader and see that it is tracking two particle groups. That the first group in the particle groups attribute is named partName, contains 8,000 particles and one tracked field. And that the second group is named decimated, contains 8,000 particles but will only output 800, and also contains one tracked field. When we're ready to output to JSON, all you have to do is call the dump to JSON method, and it will write all of the JSON files for you. If instead you would like the JSON data to be stored in a string rather than written to disk, you can use the write JSONs to disk equals false keyword argument. And it will create a very long string that contains all of the JSON data that would have been outputted to disk. Make sure you capture that output into a variable, otherwise it might break your Jupyter instance, whatever that's called. Anyway, so what I've shown here is a pretty generic use of the reader and particle group subclasses. What we've done is created an array reader subclass that will repeat all of this stuff for you in just a single initialization call. So here you can pass in any number of coordinate arrays, corresponding field arrays, and a JSON dir, and it will automatically initialize a reader that you can edit and get the particle groups from, just like we had before, but all with just a single line. If you're finding that the array reader isn't flexible enough to do what you want, like say for instance you can't get the fields to match, or it isn't adding the particle groups, consider doing it manually and then saving your reader as a separate subclass, say my custom reader. I hope that this tutorial has helped explain the Jupyter Notebook that already exists. If you have any other questions or there's something that I missed, please let me know either by submitting a GitHub issue or by sending me an email at agurvich@u.northwestern.edu. Thank you for watching, and I hope you enjoy using Firefly.